Next is Adrian Rex, who is a part-time PhD student who has returned to study after almost 40 years in industry. He likes to say that his day job, outside of the PhD, which we all know is, even if you're doing it part-time, is a full-time job. His day job is part of a small engineering consultancy, which specializes in the provision of front-end engineering design services to the construction materials industry, mainly in the areas of concrete production and the handling and storage of cementitious materials, which I believe has been the inspiration for the topic that he is investigating for his PhD, which he will share with us today.
Okay.
Over to you, Adrian.
Thank you very much, Molly. Let's bring up that thinking. Okay.
Looks good. 3 for 3.
Yeah. So thank you very much. I see this very much as part one of presentation, because I just want to present today about the ash, about characterizing the ash. This is just the initial part of the research. So today I'll be giving an overview of what is the problem I'm trying to solve, what are the characteristics of ash, and what are the learnings from the research so far, and where are we going. So this is just covering off a little bit of the research I've undertaken so far. So we'll start with the background. And one of the myths I want to dispel is that pond ash is a different material. I'm using here that, if some of you remember the Caltex ad from the 70s and 80s, sort of modified that to be ashes ain't ashes. And for those of us working with fly ash or any ash, it's important to understand, I believe, where it comes from. So we have our coal-fired boilers. We pulverize the coal to about 100 microns and blow it into the boiler, where it combusts. We obviously get energy, but we also get residual products. We get heavy particles that fall to the bottom of the boiler, which are termed bottom ash. And then the rest of the particulates head off in the flue gas. Now, what proportion goes of our coal combustion products are produced? Well, if we look at Millmerran Power Station, so just down the road from Toowoomba, for every ton of coal that's burnt, it will produce about 400 kilos of non-combustible products, of coal combustion products. So 40%, and it was as high as 46% 20 years ago, of the coal that is burnt ends up as a solid material, I don't like to say it, but a waste material. The majority of the coal that's combusted goes up with the flue gas and is called fly ash. And then it's progressively knocked out. Again, we see in Australia two types of flue gas cleaning equipment: the older electrostatic precipitators, which can be thought of as filters in series, and the more modern power stations, such as Millmerran, are running baghouses, which can be thought of as filters in parallel. These filters knock out the very fine fly ash. Let's go back to the bottom ash. What do we do with the bottom ash? So it's about 20%, depending on the power station, of the ash that's produced ends up as bottom ash. Some of that bottom ash is used, and we'll see where it is used. The remainder of it is sent to ash repositories. With the fly ash, some of it we are able to process, we are able to classify and send off as a supplementary cementitious material, mainly for use within the concrete industry. Note here it's quite a complex process. In classifying, you end up with a lot of very, very fine material, which they will choose to blend in with runner station fly ash to increase the yield. In some stations, using electrostatic precipitators, there's no need for this classifier processing, because you can select which electrostatic precipitators you want to get your fineness. As I said, an ESP can be thought of as a filter in series. So what happens to the excess fly ash? It is sent off to ash repositories for storage. It is sent off after being mixed with water. Okay, so how much of this ash do we produce every year in Australia? Well, in Australia, we burn about 80 million tonnes per year of coal, producing around 12 million tonnes of coal combustion products, of which we beneficially use just under 3 million tonnes. I use the word beneficially use because you'll see a lot of quotes in the literature, references, that Australia utilises over 50%. Well, that's not true when you look at the definition of beneficial use. A lot of the ash in Australia is used to fill the mine voids. So we produce a lot of ash in Australia. We've actually currently got over 600 million tonnes of ash in these ponds. You can't always see them, especially in Queensland, because our power stations are tucked away in the middle of nowhere. If you go down to Newcastle, New South Wales, you can see all around Lake Macquarie there, the old power stations and their huge ash ponds. And we'll look at some of those in a minute. So what do we do with the ash, the excess ash, the excess coal combustion products? Well, as we've seen, I like to think of coal combustion products, or fly ash in particular, as a family of products. It could be run of station, could be classified ash. It could just be sent to the repository. The two only methods of getting rid of your ash is to pump it, either as a lean slurry, so a lot of water and a little bit of ash, or as a dense slurry, which was pioneered in Australia, where you've got about 40% solids in your slurry that's pumped to the dams. The other method, and again, you can see this down the road at Millmerran, is you transport it, they call it dry, you transport it to a hole in the ground in a truck. When we say dry, it's still retaining about 20% moisture, because you need to stop this material from blowing away. You need to condition it. What do these repositories look like? The one on the right there is a typical ash repository. It's about 1 kilometre by 1 kilometre, and sometimes there'll be several ponds of that size at a power station. The one on the left is the infamous Tennessee Valley Authority Kingston Power Station repository built above ground. To give you an idea of the scale, if you peer at your screen very carefully, you'll see down here tiny cars. That repository is massive, and you'll appreciate that when it gave way, when the wall collapsed, the sort of damage it could do, it did. And that's what, Molly, about 10 years ago, I think that happened. And they're still rehabilitating the ground. Ash repositories do fail. Typical ash repositories, you can see different ones here, a bit of a moonscape. You get washouts. This one here is in the back of Ipswich. You can see that there is some vegetation, but still a very powdery surface. Right, so what does this cause? Storage of the ash presents some environmental and community health issues. In an active ash repository, you've got dust. We just saw that the surface there can be quite dusty. The fly ash, well, all these ashes are less than 100 micron. They're respirable dust, high crystalline silica, which rings alarm bells. And of course, you're getting stormwater, you're getting rain. And there are studies from the US and from India in particular that have shown leaching of heavy metals into the groundwater. So we're seeing community health issues in terms of dust, in terms of polluting the groundwater, in terms of the whole food chain uptaking these heavy metals. So my project is very much about, well, what can we do? What can we do with these deactivated repositories? There are two current techniques used. One of them is capping, and that will solve the problem of nuisance dust emissions. You're capping it with a clay and then vegetating it. Well, that doesn't solve all your problem, because if your repository is below the water table, you're still going to get water flowing through it. That brings us to the second rehabilitation technique, which is to dig these out and put them into new lined ponds. And that's currently occurring in the US. The cost is billions. As I said, in Australia, we have 600 million tons stored. Those repositories are still mainly owned by us, the taxpayer. When they sold the power stations off, the state governments kept ownership of the ash ponds. And as we're closing the power stations down over the next 10 to 15 years, we've got to look at doing something with these ash repositories. Okay, which brings us to what's the project aim? Well, these ash ponds are going to be with us for decades, for generations, 600 million tons, even using as an SCM, and we're using 3 million at the moment. That's a lot of years. In the meantime, we're going to continue to leach into the groundwater, potentially leach heavy metals into the groundwater. So one potential solution is to create a sealed layer in the bottom of the ash ponds. Now, these ash ponds can be 8, 10, 20 meters deep. So the aim of the project is to investigate whether we can, in fact, produce an impermeable layer at the bottom of the ash pond that stops the leaching of potentially contaminated water into the groundwater. And that should buy us time to use this great resource. As we've seen already today, fly ash is in demand as an SCM, as a supplementary cementitious material. So can we, in fact, create a geopolymer sealant at the bottom of the ash pond that prevents the movement of rain into the underlying groundwater? The equipment to do this is readily available for soil improvement, whether it's jet grouting or the deep soil mixing. So the concept is we inject the activator down into the bottom of the ash pond, mix it up, and in situ create this layer. Okay. We don't have a lot of choice with the ash that we're using. It is what it is. Unlike previous work on geopolymers, we've got to make do with the ash that is there, the particle size distribution and the chemistry. We do have advantages, though, over traditional geopolymers. The curing time, we're not concerned about early curing. We can cure the geopolymer over days or weeks. A low strength is acceptable. Should also say one of the differences is ambient curing. The geopolymer material is cured under ambient conditions. So what do we need from the properties of this liner? It needs to have a low permeability. It needs to be durable, and in itself, it cannot create another environmental problem. And of course, given the size of these ash ponds, it's got to be a low-cost material. So let's look at the major factors affecting geopolymer performance. We have a precursor, or the fly ash. The properties are affected by the mineralogy, the surface area available for reaction, the workability, which is a function of particle size distribution, particle packing, and the porosity. We've got the activator, the alkali activator, and here we can control the chemistry of the activator and the temperature. So one of the questions I've been looking at is, we cannot cure at increased temperature, but what happens if the activator temperature is increased? How does that affect performance? The activator in this case I've been using is sodium hydroxide and sodium silicate. And of course, curing temperature and time, what are its effects on our performance? Right, let's look at mineralogy. We're seeing here 5 Australian ashes. And you can see there's quite a wide range of chemical composition. Australian ashes are all low calcium composition. The reactivity tends to increase as we move this way. So we've got quite a range. This ash here is actually considered Australian's best ash. And not only is it the chemistry, but it's also, as we will see, the particle size distribution and particle shape. Now, does the mineralogy change depending on particle size? Well, we can see here there's not a lot of difference. In fact is, I began to wonder when I put this slide up, had I just copied the data by accident? But no, you can see peaks here are of different intensity. So I was a bit worried there that I just copied and pasted. But no, so we're not seeing a significant difference in mineralogy between the different particle size distributions. A little bit of diversion here. I like ternary diagrams. They're a very good way of looking at the composition of a complex material. If you look at the literature, unfortunately, you'll see many ternary diagrams here plotting the major constituents of cementitious materials: calcium, silica, and alumina. Please remember that those 3 materials do not sum to 1, their composition. So when we look in the literature and we see people drawing these ternary diagrams, they've normalized them by accident. They've relied on the software. These 3 could add up to only 0.4. So if we look at a modified, well, a more correct ternary diagram here on the right, we can see the Australian ashes here are what's termed an ASTM class F. This class C here is actually a New Zealand ash. We've got slag, we've got cement. So increasing reactivity that way. Notice here that all the stuff that isn't calcium, alumina, or silica just shown in this axis. So that's just a personal bugbear of mine. When I see these drawings here on the left in papers, people are not thinking about how they're plotting. Okay, so that's the mineralogy. The mineralogy changes slightly with time. So we can see these data points here. There is a slight change in mineralogy with time as it comes out of the station, and we'd expect that to be reflected in the ash ponds as well, that over time the mineralogy will change slightly. Particle packing, very important. The workability, and anyone who's played with fly ash, and particularly bulk fly ash, quickly learns that different ashes have a different water demand when they're making their concrete. You can't just substitute one ash for another because the workability is affected, the water demand is affected. So how do we qualify this? Well, developed a test from the soil people. And this is, I haven't got the latest apparatus here, This is the Mark 1. We've got a more complex method now, again, based on our friends in the soils research area, that sort of quantifies the amount of water that's needed, that the ash can hold on itself, both within the pores and on the surface of the particles. The geopolymers, of course, require liquids for reaction, which is what our activators are, but also to provide lubrication between the particles for workability, as is needed in concrete. And look, if we look at this graph here, we've got water holding capacity, so the amount of water that is held within the ash particles and between the ash particles, plotted against the spread for a standard concrete mix. So we saw earlier on this morning Stephen's presentation where he was measuring the spread of concrete. So you adjust the water content to get an equal spread in his case. Here with a constant, here we've got a constant spread and the water content has been increased until we get a constant spread. And perhaps not surprisingly, there's a pretty good relationship there between water holder capacity and the water required to get the same spread. So, because what we're seeing is that ashes with similar particle size distribution give us geopolymers with quite different flowability. Some ashes are very, very watery, flow very easily, and with that same amount of liquid, we've got others that are very dry, sand-like material. Okay, so what is happening to the particle size distribution? We see in certainly a lean slurry deposit system, we see distinct layers. You can see layers here in the cut I put through the ash pond, and there's a mechanism there of sedimentation of particles being pumped. They flow across the surface of the pond. Once you stop ponding, you then get evaporation and deposition. So you can see here in the B layer, very, very narrow particle size distribution. So as we've pumped there, it's like a beach. We've pumped down, we get coarse particles here and increasingly fine particles as we move further away. Again, sedimentation theory. If we look at the particle size distributions, and yes, I know this graph's difficult to read, you can see there's quite a wide range of particle size distributions between the different ashes under test. So in an ash pond, there's a long ash pond, pump in there, we see different particle size. There's at different locations within the ash pond and also at different depths within the ash pond. So an ash pond is not homogeneous. Many researchers assume that one sample taken there is representative of the whole ash pond. That's not the case. Not the case. And that makes the reclaiming of these ash ponds over the next couple of generations quite a challenge. Because you can have some nice fine material there and some coarse material up that end. Do you blend it? Yes. Some quite interesting results when we began to look at the density for different particles or different sieved particle size. We actually see for 3 different samples here, this sort of curve here. So what's happening? What I believe is happening, as their evidence, is that we've got solid particles there, and we'll see this in a minute. Solid particles there, and then in the middle here, we've got some solid particles and some empty hollow spheres. And the number of empty hollow spheres, or cenospheres, that proportion of cenospheres in the mix rises and drops off. So ash particles are not all the same. So there's one way we can't measure the surface area. You cannot say, well, the surface area, specific surface area is not equal to, what's it? Density, wait a minute, I'm going to get this wrong. 1 over the density times the particle diameter. Because that density is not constant. The density varies depending on the particle size. Let's have a look at some of the particles. For start, ash particles are not all spheres. Yes, the ones on the left are nice spheres, but look at the potatoes here on the right. And we see a lot of ash samples where they're not spheres, they're potatoes. And by the way, I'm looking for a better named potato to use in research papers, so I'm open to suggestions, please. These are bottom ash particles, and you can see these ones here are quite porous, and again, they're not spheres. And as we saw earlier on, many power stations will blend bottom ash, this stuff, with the more solid particles and pump to your ash ponds. We also have, as we said, cenospheres. So you can see here these hollow spheres. Yes, thanks, Polly. So we can see these hollow spheres here on the left. On the right here, what's called a plerosphere. Plerosphere is a hollow sphere with other spheres inside it. In fact, some of these spheres inside it are themselves plerospheres themselves. So a little bit like Russian nesting dolls. You can see there that the wall on the cenospheres, some of them are quite porous. On the plerosphere here, that wall is quite solid. So these samples were all done on the baby Joel. Great piece of kit. And I mounted these, the ash particles, and then sat in front of the TV hand polishing them. Hand polishing down at this micron level is proved very successful in being able to see what's inside an ash particle, to get a better idea of what's going on with the ash particles. Well, what are the learnings and what I'd like to pass on to people? Well, we've seen that cold combustion products are stored in ash repositories, 600 million tonnes in Australia, over 2 billion tonnes in the US, and probably more than that in India. We're not going to be using that much ash for it'll take us generations to consume it, even when we've closed our power stations. And these ash repositories pose an environmental, will impact the environment and impact community health due to, as we said, nuisance dust and leachate. Ash particles are not all the same. When we get ash from a power station, we've got to ask, where does it come from? Is it run of station? Is it classified? Is it repository ash? Is it conditioned ash? We must think of fly ash as a family of materials. Sometimes we will receive ash from electrostatic precipitators. That has a completely different size distribution to what we would expect out of a baghouse. Pond ash mainly contains fly ash. Over 80% of the material that goes into our ash ponds is in fact fly ash. So pond ash is not a different material. It is a fly ash. And one of the challenges facing the industry is, how do we get that fly ash back out of the ponds? It is wet. That's the main challenge. We're talking anywhere between 50 and 120% moisture. Ash particles are not solid spheres, as much as we'd like to, especially consider them to be spheres, especially when we're using them as a lubricant in pumps. We've seen that some of them are potatoes or whatever Molly's Polly will say, aspherical. So the current work, future work I'm working on is the permeability. As we said, this sealant must be impermeable. So again, we got a permeameter is built and is under testing, looking at the porosity of the geopolymers and looking at the durability testing of geopolymer. But the main thing I want to get across today is that ashes ain't ashes. If you're using an ash, ask where it comes from. Bulk ash is quite different to what you get in your bags of ash. The people who sell you the bags of ash will tell you it is sweepings off the floor. There's no guarantee of from bag to bag what the composition of that ash is, because it's a blend of ashes from several different power stations. So if you're wanting to do research using ash, highly recommend talking to one of the cement companies and getting it from a bulk sample, not from a bag that you buy in Bunnings. So thank you very much. Anyway, that's a quick overview of part of my research that I've undertaken.